All right, so as we just said, with work energy theorem, when in any of those problems, the work being done is changing the mechanical energy. In the problems we're about to look at, the mechanical energy is not changing. Okay? The potential and the kinetic might change, but they change into each other. Okay? Meaning that the total mechanical energy remains the same. So we got to review a little bit here from kind of the first day of the unit. Okay? Mechanical energy is the sum total of an object's kinetic and potential energies. Okay? So if you've got a plane flying through the air, that plane has potential energy because it's above the ground, and it's got kinetic energy because it's moving. Its mechanical energy is the sum of those two energies. Everybody follow me there? Okay, are we going to use the same formulas here? We are. We still calculate kinetic energy using 1/2 mv squared. We still calculate potential energy with mgh. That part's what's going to seem the same. Okay? The part that's different is instead of work is a change in energy, now no work is being done. So if no work is being done, the energy doesn't change. It stays the same. So conservation of energy questions start out like this. EI equals EF. Okay? What we've been doing is subtracting EI from EF to find the difference. If I do that in these questions, the difference will be 0, because there's no change in mechanical energy. All right. So this first paragraph here is just a review of work and the definition of mechanical energy. So mechanical energy is the total amount of kinetic and potential energy that an object has. All right, so if I have a 0.3 kilogram baseball thrown in a straight line through the air, which is physically impossible, but we'll pretend it happened, okay, because you cannot throw something in a straight line. Why not? What will it always be doing? Falling, yeah. You can't throw something in a straight line. Okay? Gravity will grab it. As soon as you throw it, gravity will grab it, okay, and it'll start falling. Now, if you throw it really fast, you might not see that falling very much, but it's happening. All right? If you've ever, done any archery, okay, shot at a target with a bow and arrow, you cannot aim for the bullseye. You will never hit it if you aim for it, unless you're standing this far from it. Okay? And then you have a pretty good chance of hitting it, actually. Right? But if it's any distance away, the arrow falls as it flies through the air. Right? Okay, so this baseball, imaginary baseball, is thrown in a straight line through the air. And it's a height of 2.5 meters above the surface of the earth and moving at 20 meters per second. What's the total mechanical energy of the baseball? So, we know that mechanical energy is the object's potential and kinetic energies added together. So all we have to do is plug into our formulas to calculate the kinetic energy and calculate the potential energy. Okay, so when we do that, right, we'll calculate the kinetic energy by going 1/2 times 0.3, which was the mass, times 20 squared, plus 0.3, the mass, times 9.81, that's G, times 2.5, that's H. Right, so we get that it had 60 joules of kinetic, 7.36 joules of potential, for a total of 67.4 joules of mechanical energy. Okay, is that a pretty easy calculation to do? Okay. All right, I would like you guys to try questions 8, 9, and 10. They involve this formula. Plus the formulas we learned from last week. Okay, so you'll need all of those formulas. Most of them are just asking, calculate, like here's the mechanical, calculate one of the two. Or here are the two, calculate the mechanical. Right? It's really one or the other. All right, I'll give you a few minutes to work on those, and then we'll walk through them together. For our first one here, okay, we're just following this formula right here. EM equals EP plus EK. Have it on the next page here, right? Figured, no, okay. So we're just calculating what our total mechanical energy is, okay, and we're just going to plug in our formulas. So we're going to have m times g times h, so that'll be 0.3, because our mass needs to be in kilograms. That's the trick to this question, is mass is always in kilograms for this. Okay, times 9.81 times 30 meters. Okay, so that'll get us our EP, and then for our EK, 1/2 times 0.3 again, times 8 squared. Right, when we put all those together, we should get 97.89 joules worth of mechanical energy this time. Okay, now with 9 and 10, they give you the mechanical energy in 9 and 10, and they're asking you to solve for either EP or EK. All right, give you a couple more minutes on those. We'll go through those, and then I'll ask you to do one more step with 9 and 10. Okay, so we know the mechanical energy is 3,000 joules. And we know the mass is 55 kilograms. And we know the speed is 8.33 meters per second. All right, if I have m and v, can I calculate kinetic energy? I can, because the kinetic energy formula is 1/2 mv squared. So if they want me to calculate EP, all I have to do with EK is what? Subtract it, do the opposite if I want to move, right? I want to isolate EP, so I'm going to subtract EK over to the other side. So I'll have mechanical minus kinetic equals potential. And then all I have to do is put my numbers in. So I'll have my 3,000 joules of mechanical energy minus 1/2 times 55 times 8.33 squared. Okay, that'll get me the kinetic energy, and then that'll leave me with the potential. So if I punch all that in, okay, so 3,000 minus 0.5 times 55 times 8.33 squared. Okay, I get 1,091.8 joules.
What's the exponent on number 10?
The exponent on number 10 is 3.
Thank you.
Yeah. Okay, everybody all right with that one? Okay, now before you get going on the next one, here's the next step in this. If I were asking that question, I would not ask for the potential energy. I would ask for how far above the ground the high jumper will jump. Can I calculate that? I can, because what did I just calculate? I calculated the potential energy, okay? And it was 1,091.8 joules. Well, that also happens to be calculated by using this formula. Would you agree? Do I have m and g? Yeah, I always have g. It's always 9.81. So could I very easily from here calculate the height? I could. I just have to divide by m times g, and that'll give me the height. So if I take that number I just calculated and divide it by 55 times 9.81, m times g, I will get that high jumper is jumping over 2 meters. Okay? And I will bet you nobody does that outside today. I coached track for 20 years. I only saw a few people ever go over 2 meters. It is impressive. Okay? 2 meters is like 6 foot 7, something like that. Okay? It's pretty impressive to go that high. Okay. Give number 10 a try here. I'll give you a couple more minutes, okay, and then we'll go over number 10. So on number 10, we have a construction worker who drops a hammer. Okay, we know the mass of the hammer. Okay, is 2 kilograms, and we know that when the hammer is 50 meters above the ground, okay, that it has 1,880 joules of mechanical energy. Okay, we want to calculate the kinetic energy of the hammer. So if mechanical energy equals EP plus EK, and I know the mass and the height, can I calculate the potential? And they told me the mechanical. So if I want to isolate EK, all I do is subtract EP over to the other side. Okay, so then I plug in my numbers here. I got 1,880 minus 2 times 9.81 times 50. That's mgh. Okay, so I'm calculating the potential energy with that. That will leave me with the kinetic energy when I subtract it from 1,880. So 1,880 minus 2 times 9.81 times 50. Okay, so 899 joules worth of potential energy. Or sorry, kinetic energy. Sorry. Okay, so if I know that that's the kinetic energy, and this were me asking the question, I would not ask you for the kinetic energy, I would ask you for the speed. So now that I know the kinetic energy, could I easily calculate the speed? I could, because I have the formula for kinetic energy. Okay, I know that that 899 joules equals EK, which equals 1/2 mv squared. Can I solve for V? Yeah, I know the mass, right? So I just go 1/2 times 2. Okay, so that's easy. The square root of 899 is 30. Okay, because I have to square root this, okay, in order to get V, right? Half of 2 is 1. 899 divided by 1 is 899. Take the square root of that and you're going to get 29.999 or something like that. Okay, it'll round to 30, okay, meters per second. Okay. Everybody all right with that? Okay. Now, well, let's have a look at this. This is kind of combining the two concepts, work energy theorem with conservation of energy. Okay, so I use 100 newtons worth of force to pull back a bowstring 1/2 meter, and I aim the bow vertically, so I do this. All right, how much work have I done? I use 100 newtons of force, I pull it back 1/2 meter. How much work have I done? How do we calculate work again? Force times distance. What's 100 times 1/2? 50. Okay, force times distance. 100 times 0.5 is 50. All right, so I did 50 joules worth of work. How much potential energy is in the bow? Don't overthink it.
50 joules.
50 joules. I just pulled back the bow, right? This is like the lab we did last week where we pulled on the rubber band. Okay, if I stretch the bow, I pull back on the bow and I do 50 joules worth of work, that 50 joules is now the elastic potential energy within the bow. Okay, now here's where it kind of combines with conservation of energy. If I fire the arrow, how much energy will the arrow have? 50 joules. Okay, energy cannot be created and it cannot be destroyed, therefore it must be conserved. Okay, law of conservation of energy says if I do 50 joules worth of work, there are always going to be 50 joules worth of mechanical energy in that bow arrow system. Okay, in the real world, you always lose some to heat and sound and all that other stuff, but okay, we're dealing with the perfect physical world here. Okay, so how much kinetic energy does it have when it leaves the bow? 50 joules. What's the potential energy at its highest position? So if I shoot that arrow straight up in the air, it's going to do this. It's going to go up, 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 and then it's going to stop at its maximum height before falling back down to the ground. So when it's here, its maximum height, and it's for an instant stopped, all of its energy is what? In what form? Since it's stopped. Potential, yeah. It would have all potential energy. How much? 50 joules. Okay, so this is the basis for the law of conservation of mechanical energy. Energy can't be created and it can't be destroyed. It can be converted though. It can be changed from kinetic to potential and back again. Right? It can be used to do work on something else. Right? It can be changed into heat and sound and all that other stuff. Right? But when it comes right down to it in its simplest form, If I put 50 joules worth of work into a system, that system will have 50 joules worth of work, or worth of energy to do whatever it wishes with. Okay? If it's a bow and arrow or a slingshot, then it's gonna convert it from elastic potential to kinetic, to gravitational potential, or whatever. Okay? But it's always gonna be, in total, 50 joules. Okay? All right. Oh, where did it go? Ooh, that book was crooked when I scanned it. Okay, you can still read it though. Okay, so the law of conservation of energy states the amount of energy in any given situation is constant, because energy can't be created or destroyed. It can be used to do work, but it's still going to be accounted for. Okay, so if we do this example here, okay, where I drop a rock over a cliff. So if I'm just holding the rock out over the cliff, when I'm holding it there, does it have energy? It's got potential energy. If I drop it, what's going to happen? It's going to fall, yeah. And when it falls, it's going to accelerate downwards, which means it's going to go from a speed of 0, in other words, no kinetic energy, to some much greater speed than that. But what's going to happen to its height the entire time? It's going to decrease. So here's what we start with. Okay? We start with a lot of kinetic, with a lot of potential energy at the top of the cliff and no kinetic. And as the rock falls, those two things convert into each other. They pass each other about halfway down, okay? And then after the halfway point, we see more and more kinetic energy as it goes faster and faster, but less and less potential energy because our height is getting smaller and smaller, okay? And all that's happening here is the potential is converting into the kinetic, meaning that the total mechanical energy is staying the same because I'm not doing any work. When I drop it, I've already done the work. I carried it to the top of the cliff. I did all the work. Okay? When I drop it, the energy it had from my work has to stay with it. It's just not going to be potential because as it falls, it'll have less and less potential as the height goes down. But it'll get more and more kinetic as the speed goes up. All right? So they just convert back and forth into each other. If you ride a roller coaster, that's what happens, right? You get towed up to the top of the first hill, and then you go down the first hill, and you go up the next hill, and okay? So I do all the work here. I get a certain amount of energy, and then as I go down the hill, I still have that much energy. That's why I'm going so fast at the bottom. Okay? It all gets turned into kinetic instead of potential, right? And then as I go back up this hill, my speed decreases, right? But my potential energy gets bigger, and then so on and so on as I go along the ride. But my total mechanical energy remains the same throughout. Okay? So if we look at this question here, and we got a 1.5 kilogram rock that's dropped from a height of 30 meters, should we be able to calculate the speed of the rock just as it hits the surface? We should, because we know the energy when it's dropped and the energy when it hits the lake are the same. They're equal. That's what the law of conservation of energy says. It says that my initial mechanical energy equals my final mechanical energy. Okay, now we just did a bunch of questions where we learned about how we calculate mechanical energy. Mechanical energy is potential energy plus kinetic. Okay, so what we're saying here is this is our initial mechanical energy, the sum of the object's potential and kinetic. Okay? On this side is the object's final mechanical energy, the sum of its potential and kinetic. Everybody all right with that? Okay. In this situation, how much initial kinetic energy did the rock have? So I'm holding it out over the cliff. How much kinetic energy does it have at that point? How much kinetic energy does my pen have right now?
Zero.
None, because it's not moving. Okay, so we got no initial kinetic energy. The end of the question is when it hits the lake. Well, if the height's measured from the lake, when I hit the lake, what's my height? 0. So how much potential energy do I have when I hit the lake? 0. So what we're saying here is the initial mechanical equals the final mechanical, but in this situation, that means the initial potential equals the final kinetic. Okay, because we didn't have the other two types. So, do I have formulas that calculate those two types of energy? Okay. Okay, I'm progressing along here, but am I still saying exactly the same thing each time I write something? Yeah, I'm still saying my initial energy equals my final energy. I'm just becoming more detailed as I go along. All right, this question wants me to calculate VF. So how do I get VF by itself? Divide what? Half of M, right. Now if I do that, what happens to the M's? Yeah, they cancel. Is that kind of strange? Here's why it might seem strange, but isn't strange. All things fall at the same rate. Okay, remember I showed you the bowling ball and the feather? Okay, all things fall at the same rate regardless of their mass. That's why mass cancels. It doesn't affect the final speed. Okay. All right, so those two things are gone. So now I've got GHI over 1/2 equals V squared. What do I want? I just want V. So square root that, and I got V. Okay, so that's what they're doing here. Okay, they write it a little bit differently. I don't like writing the 2GH part. Okay, so when we punch all this in, we'll have 9.81 times 30 meters. That was the height of the cliff, divided by 1/2, which is the same as multiplying by 2. Okay, that'll give me VF. So when I punch in my numbers here, so the rock will be moving at 24.3 meters per second when it hits the lake. Everybody all right with that? All right. So they get a little bit more complex as we go along, but we'll kind of start with these ones here. Anytime something is dropped, its initial kinetic energy is 0, because it's not moving. Okay? And anytime something hits the ground, its potential energy is 0. Okay. Then I would like you guys to try number 11. It's very much like this one. Okay, so try number 11 first. Okay, and we'll go over it and then we'll look at number 12. No. Okay. All right, are we ready to look at 11? So for number 11, right, we know the mass, 10 kilograms. Okay, and we know that it's dropped from a height of 12 meters. Okay, calculate the speed of the balloon just before it hits the ground. So basically when the height is 0. Okay, so that's what I know. Now, according to the law of conservation of energy, does the amount of energy it has when it's dropped equal the amount of energy it has when it hits the ground? That's what it says. Okay, so I can start this out with EI equals EF. Okay, so that's initial mechanical equals final mechanical. We know that to calculate mechanical energy, we add our potential and kinetic energies together. Okay, so every law of conservation of energy question is going to start this way. Okay? Doesn't matter how complex it is, that's how it's going to start. Now from here, I can cancel off some of those energies because some of them are 0. Okay? So for example, the question tells me that the water balloon was dropped. How fast is something moving if it's dropped? That's its rate of acceleration. How fast is it moving right now? 0. Okay? It's not moving yet, right? Okay? Anytime something's dropped, its initial velocity is 0, which means its initial kinetic energy is also 0. So, there isn't any of that. When something hits the ground, what's its final height? 0. So what's its final potential energy? 0, because potential energy is mass times gravity times height. So we don't have any of that. Right? So what we're left with is the same thing we were left with for the example. The initial potential equals the final kinetic. Right? And I have formulas for both of those types of energy. Okay? This one is m times g times h, initial, equals 1/2 mv final squared. And I'm trying to find v final. So I divide both sides by 1/2 of m. M is on the top and the bottom, but if you don't want to cancel it, it's fine. They did, after all, give it to you, okay? But it does cancel. And then I've got to square root that in order to get VF. So VF will be the square root of 9.81 times the initial height, which was 12 meters, divided by 1/2. So when I do that, okay, so square root of 9.81 times 12 divided by 0.5. I get 15.3 meters per second. Okay? Everybody all right with that? Okay. Is the math kind of similar to what we did in the work energy theorem ones? It's similar. It's all algebra. And these ones are also patterned. Okay? I just told you a minute ago, every one of them starts the same way, EI equals EF, and then you put in all of the energies and you cancel off any that are 0. Okay? These are all very patterned, so as long as you can do the algebra and read the question, you shouldn't have any trouble with them. All right, how many people are done the second one? Okay, take a few minutes here and work on the second one. The answer is there. If you got 0.13 meters, you did it right. That seems a bit ridiculous because that's only this high off the trampoline, but it's a little kid. And they're not moving very fast when they go off the trampoline. 1.6 meters per second is not very fast, so okay, they're not going to get very high. This trampoline is one of those trampolines that's set into the ground. Okay, so the trampoline is at a height of 0. Okay, so considering they're on the trampoline, their height is 0. This trampoline is set into the ground, so our initial height is 0 meters. All right, so we've got this information. We're looking for the final height. Now, the maximum height to which they rise is going to look like this. They go up in the air, and as they go up, they slow. How fast are they going when they're at their maximum height? 0, because they slow down, slow down, slow down. So at their maximum height, they don't have any kinetic. It's all potential. Okay, so that's something we have to get from the context of the question and from an understanding of how things move. All right, they're not going to always outright tell us everything. Okay. So, initial mechanical equals final mechanical, so this is the pattern. Okay, initial potential plus initial kinetic equals final potential plus final kinetic. Okay, our initial potential is what? Since we start at ground level, our initial potential is 0, so it cancels off. Okay, since we're at our maximum height at the end, our final kinetic is also 0. Alright, so that simplifies this down to the initial kinetic energy equals the final potential energy. So 1/2 mvi squared equals m times g times h final. Alright, so all I have to do is find h final. So what do I do with the m and the g? How do I move mg? Divide it over, because I'm multiplying. Okay, that means the m is going to cancel. Alright, so I'm going to be left with my final height equals 1/2 times the initial speed squared divided by g. So 1/2 times 1.6 squared divided by 9.81. Okay, I punch that into my calculator, 0.5 times 1.6 squared. Okay, divide that by 9.81. 0.13 meters is how high off the trampoline this person gets. Not very high. Okay, everybody all right with what we did there? Okay. As long as no work is being done, and none of these questions gave us force, none of these questions gave us distance, we know there's no work going on, okay? Then we can say the initial energy and the final energy are equal. Okay, and that is the potential plus kinetic equals the potential plus the kinetic. All right, I would like you guys to try that one. We might not get to finishing it today, but give it a try. We've done one just like it. You could refer back to an example you had in the notes if you needed